you for our 11th session of Math 7502, Mathematics for Data Science. And what we're doing this evening is a couple of things, but the first one is we are going to cover solutions to the quiz that you did, I suppose, on the 19th. Is that correct? If I look at this page, maybe you did this on the 19th. So anyway, I believe it was quite recent for you. And so that's what we'll do this evening. And then once we're done talking about solutions to these 6 problems, if we have time, then we'll go on to discuss your project, your final project of the course. Okay, so over to you, Walla. Are you ready? Okay, thanks. And I'll be back for question 4.
Yeah, hi everybody. Today we will discuss quiz 3. I will go over question 1 to up to 3. Let's now start with the question 1. In the question 1, they ask, consider the vector u equal 1, 2 transpose, and the vector v equal 1, 10 transpose. Let the matrix A be the outer product A, which equal u times v transpose. Determine the eigenvalues of A. So we need to find the eigenvalue of A. This is an easy question, and I hope all of you can solve it easily. In question 1, they give you 2 vectors. The first one, u equal 1 and 2 transpose, and the second one, v equal 1 and 10 transpose. We need to find the matrix A, where the matrix A is defined by u times v transpose. This is an outer product between u and v. So this is, here we have 2 items, and here we have 2 items. A is a matrix. The dimension of this matrix is 2 by 2. So to find the matrix A, we need to find the outer product between 1 and 2, multiply with 1 and 10. How we can find the outer product? We need to multiply here 1 times 1, which equal 1. 1 times 10, here 10. 2 times 1, 2, and 2 times 10 is 20. This is the matrix A. The dimension of this matrix is 2 times 2. Now we need to find the eigenvalues of this matrix. To find the eigenvalues, we need to follow this equation, which say determinant of A minus lambda I equals 0. So we need to find the determinant of this matrix after subtract lambda from the diagonal. So let's try to find it. We need to substitute here to find the value of lambda. So we need to find the lambda here, 1 minus lambda. Here we have 10, here we have 2, here we have 20 minus lambda. This is equal to 0. To find the value of lambda, we need to find the value of this determinant. So we need to multiply 1 minus lambda, multiply with 20 minus lambda, and this is minus 2 times 10, which equal 20. This is equal to 0. After that, we need to expand to find the value of lambdas. Here we have 20 minus lambda minus 20 lambda minus 20. This is equal to 0. If you look here, we have 20 minus 20, this is 0. And here we have, this is plus, sorry, here lambda squared, because lambda squared, this is positive. So we have lambda squared minus 20, okay, just to be sure, 1 times 21 times lambda, okay, check again. 1 times 20, 20, 1 times lambda minus 20 lambda plus lambda squared minus 20 equal to 0. So here we have 20 minus 21 lambda plus lambda squared minus 20 equal to 0. Here we have 20 minus 20 equal to 0. So here we have lambda squared minus 21 lambda equal to 0. You can take lambda as a common factor. So if you take lambda as a common factor, it remains lambda minus 21 equal to 0. So the value of lambda equal to 0 or lambda equal 21. So the value of lambda equal 0 or lambda equal 21. Okay. If you look back to the matrix A, here we got the value of lambda. The value of lambda 1 is 0 and 1 is the 21. If you look back to the matrix A, do you think there is any relationship between the matrix A and the values of lambda? If you look here and try to find the trace of this matrix, the trace of this matrix is the 20 plus 1 is the sum of numbers in the diagonal. 20 plus 1 equal 21, which is the same as the value of lambda here, which equal 21. In addition, if you look to matrix A, here we have in the first row, we have 1 and 10. And in the second row, we have 2 and 20. If you multiply the first row by 2, you will get the second row. So this matrix with rank 1, because we can write the second row as a linear combination of the first row. So the rank also of this matrix is 1. Okay, this is the solution for question 1. It's enough to show the value of lambda is 0 and lambda is 21. We need all of these explanation, and you need to be familiar for this to find the solution in part 2. Okay. Now let's move to part 2. Okay. In question 2, they ask, now set U equal 1, 2, 3, 4, 5 transpose. If you remember, in part A, we have U just 1 and 2. Here we have 1 up to 5. And V equal 1, 10, 10 to power 2, 10 to power 3, 10 to power 4. But in part A, just we have 1 and 10. With these values, determine the eigenvalues of A, which equal U times V transpose. They give you a hint. Remember that the sum of the eigenvalues is the trace of the matrix. Okay? They give you a hint, so it's easy for you to solve it. In question 2, they give you that the value of U equal 1, 2, 3, 4, 5 transpose, and the value of V equal 1, 10, 10 to power 2, 10 to power 3, 10 to power 4. If you look here and try to find the matrix A, the dimension of this matrix is 5 times 5, because here we have 5 entries, and here we have also 5 entries. So the after product of U times V transpose, this matrix is 5 times 5. And it's difficult for us to find the determinant of this matrix. So we need to use something which is familiar for us. We need to find the rank of this matrix. If you remember from part A, when we have just 1 and 10, 2 and 20, we said that the rank of this matrix is 1. The same thing here. The rank of this matrix also 1. So the rank of the matrix A is the same, because in part A just we have 1 and 2 and 1 and 10. But here just we put some numbers, and the rank is this matrix is the same. So the rank of matrix A equal 1. The rank of matrix A equal 1. Because we have matrix A, which is 5 times 5, and the rank is 1, so there is 4 entries of this matrix in the diagonal, which equal to 0. So here we have 4 eigenvalues, which equal to 0. Because here just rank equal 1, so just we have 1 number, and 4 lambdas equal 0. So here we have, because the rank of matrix equal to 1, so here we have 4 lambdas equal to 0. So there is 4 lambdas which equal to 0. So we have lambda 1 equals 0, lambda 2 equals 0, lambda 3 equals 0, and lambda 4 equal to 0. So just we need to find the last value. We need to find the value of lambda 5. So just we need to find lambda 5. We need the value of lambda 5. Okay? So we need to find the trace of this matrix. We have 4 lambdas is equal to 0, and we have lambda 5. If we have a matrix A, the matrix A, we have 0, 0, 0, 0, and we have lambda 5. To find the value of lambda 5, we need to use the trace of the matrix. Okay, we need to add the sum these together to find the value of lambda 5. And the trace, if we have an outer product, because here we have U times V transpose, the trace of an outer product, it's equivalent to the dot product between these vectors. So the trace equal trace for outer product equal the same as inner product. So to find the value of lambda 5, just you need to multiply these vectors together and add the numbers to find the value of lambda 5. So we need to multiply 1, 2, 3, 4, and 5. We need to multiply it with 1, 10, 10 to power 2, 10 to power 3, and 10 to power 4. 1 times 1 here we have 1 plus 2 times 10 plus 3 times 10 to power 2 plus 4 multiply with 10 to power 3 plus 5 multiply with 10 to power 4. Okay? And add it together. You will get the value here is 54,321. So this is the values of lambda. We have 4 zeros and 1 number, which is 54,321. Okay. If you don't know how to find the relationship between trace of outer product and inner product, you can try to find here. If you try to find the multiplication between these together, here we have 1 times 1 is 1, 2 times 10 is 21, which is the same here. We get 1 lambda is 0, and the second one is 21, which is the same as the inner product between these two vectors. Okay. Now let's move to the third part. In third part, they ask, let B be an 3 times 2 matrix with rank of B equal 2, and set the vector C equal 0, 1, 1 transpose. Assume that B multiply with B transpose times B, and all of these inverse multiply with B transpose equal this matrix. We need to find two things. The first one, let X star be the value of X that minimize the norm of Bx minus C. Determine the value of Bx star. This is the first thing. We need to find the value of Bx star. And then we need to find the value of norm of Bx star minus C. Let's try to find the solution together. They give you the matrix B is 3 times 2 matrix. And they give you that the rank of this matrix equal 2. And they give you that C equal 0, 1, 1 transpose. And they give you that the value of B multiply with B transpose times B, all of its inverse multiply with B transpose equal 1, 0, 0, 0, half, and half. Here we have 0, half, and half. And X star is the minimum point. We need to find the value of the first thing. We need to find the value of B X star. If you look here, we have B multiply with this element, inverse multiply with B transpose. This value is the same as the value of projection. This is equal the projection matrix. So projection matrix, it's equivalent to this value. This is the first step. Projection matrix equal B times B transpose B inverse times B transpose. Okay. Now we need to find the value of X star. We learned before to find the value of X star, we used a least square, and the value of X star equal B diagram multiply with C, and B diagram equal B transpose multiply with B and all of these inverse multiply with B transpose. So it's equal this part. Okay, so just we need to substitute. We need to put the value of B diagram, which equal this part, okay, except B. So here we have X star multiply with, X star equal B transpose B and all of these inverse multiply with B transpose and all of these multiply with C. Just I substitute the value of B diagram. Now, if you look here, just we need to multiply with B. We need to multiply here with B and multiply here with B. So we can find the value of Bx star. Multiply both sides by B, you will get Bx star equal B multiply with B transpose times B inverse times B transpose times C. This is the same as the projection matrix, which is given in question 3. So here we have B multiply with X star equal the projection matrix multiply with C. So just we need to multiply these, this matrix with this vector to find the value of Bx star. This is equal. Here we have the value of P, which equal 1, 0, 0, 0, half, and a half, 0, half, and a half. This one is multiplied with 0, 1, and 1. If you try to multiply these together, you will get a vector, and the answer is 0, 1, and 1. If you look here, the value of this, the same as the value of C. Here, this vector equivalent to the value of C. This is equal the value of C. So this is the solution for part 1. Okay. If you find the solution correctly, to find the norm of Bx star minus C is easily. Why? Because you know that now that the value of C is the same as the value of Bx star. Because they ask you here, determine the value of Bx star and the value of the norm of Bx star minus C. And we get here that the value of C equal the value of Bx star. If you subtract these, you will get 0. So the answer is 0. If you try to find the norm of Bx star minus C, this is equal to 0. Here, because we found from the least square that the value of Bx star is the same as the value of C, and the norm here equal to 0. In addition, you can say that the vector C is in the column space of matrix B. Okay, that the vector C is in column space of B. And it's easy to see that here we have this value. The value of C is the same as the value of Bx star. If you try to subtract these, you will get 0. Okay, this is the solution for questions from 1 to 3. Now you can continue with Sam for the rest. And if there is enough time, we will go back to talk about something about projects.
Okay, thank you, Walla. Okay, so I'll begin with question 4 on this sheet, and I think I'll zoom in a little bit. And so hopefully it stays in focus, but we'll see. And I think what I'm going to do is just sort of, well, I'll read from this first, the problem that you saw, and then I'll sort of phrase it in a way, and then answer it, of course, right? Okay, so let's see what it says. Continuing with the same B, so that's the same B that we had previously. So what was it? 3 by 2, I believe, right? 3 by 2, and it has rank 2 as above. Okay, so prove that B transpose B is positive definite as a matrix. All right, so what I'm going to do is just show you what I've got written here, and I'll go through it line by line. Okay, so we're going to show basically that for all non-zero x, x transpose B times x. So in other words, this is our matrix M here, right? That's the same one as there. Times x is positive, all right? So that's what we're aiming to do. Now, so let's begin with what's on the left here in this expression. So we start with x transpose B times x. And we see that as bx all transposed, right? Remember, the transpose of the product swaps those around and applies the transpose on each one. And we can take that in reverse. All right, now we see, the reason we did this is because we have something transposed times the same something, right? Which we know is the norm, all squared. Okay, so that's our first observation, is that this here is the square of the norm of bx, right? So we're nearly there, right? We know that this is greater or equal to 0, but our final step here is to show that it's not 0. Okay, so we then get that it's positive. All right, so I've just got it written out here, right? So B11, B12, B21, B22, B31, B32, just so you can visualize it. Now that's got rank 2 under our assumption. And that means that we know what the row reduction looks like, right? So it looks like this. So when we row reduce it, we've got what looks like the identity matrix at the top and then a row of zeros. All right, so that tells us that since we see this row reduced form here, we know immediately that the null space of that is trivial, right? Okay, so what that means is that B times the vector x is the 0 vector if and only if x is the 0 vector. Okay, so then, but we've assumed here that x is non-zero, so that means that the norm of this is actually positive, so the square of the norm is positive. All right, so we conclude then that, so B transpose B is positive definite. Okay, let's have a look at the next one. Now they're progressively a little bit more involved as we go through. All right, question 5. Just put that into view there. Okay, question 5 says, what are the 3 eigenvalues of this projection matrix? B times B transpose B inverted times B transpose, and why? Okay, so you've got to do the actual calculations to demonstrate that. All right, and why 3 of them? Well, we've got a 3 by 2 matrix, right? So this product here should be 3 by 3, and hence we're looking for 3 eigenvalues. Okay, so knowing that, let's call this P. All right, we know that this is P, the projection matrix, from what Walla told us just earlier. And so what we want to do is multiply on the right, or I guess P times B. P is on the left, right? You've got to keep these in order. So P times B, now just subbing in P, what we've declared here. We've got B, and then we've got this inverted, and then we've got B transpose B there. All right, so these two, this one, B transpose B and B transpose B. Now this one has an inverse on it, and this one is just B transpose B. So we know that their product must be the identity matrix, right? And this is basically, this wouldn't be, this is non-zero, this matrix, right? Because we've got this defined up here with an inverse on it, so we know it's non-zero. Okay, so PB then is just plain B. All right, so we just have B. Now the next thing to observe is that we can say, well, that's just 1 times B. In other words, a scalar multiple 1 times each of the entries there, so 1 times B. Okay, then at this point we can rearrange this equation and express this in a way that looks a lot like the eigenvector and eigenvalue equation, okay? In other words, I'll just remind you. So A, how does it go again? A minus lambda I, so that's our determinant that we take, right? But when we multiply it out, then we're looking at, so we have this equals 0, but A x equal to lambda x, right? So this is our eigenvalue eigenvector equation. All right, so we want to take this here and write it in such a way that it looks a bit like this, right? So we're going somewhere. So now we take the 1b over to the left-hand side, and so we have equals 0, right? But this b is a 3x2 matrix, right? It's not a column matrix. Okay, so we're not quite there, but we're close, right? So this you might imagine, oh, that's an eigenvalue, right? Well, you've got an observation to make at this point. So now what we're going to have here is that, so we take the first column of this, P minus 1 times I times this first column gives us the 0 column, right? So this here is, that'll be a 0 matrix. So we're just taking this column by column. All right, and likewise with the second column of this matrix B, we have the same thing, right? And so now these are column matrices, and we can almost deduce that these are eigenvectors, okay? And that these are eigenvalues, both being the same, of course. All right, so let's have a look. Now, let's notice that the rank here is 2, so we're given that. And what that means is that the dimension of the column space is equal to 2. Okay, so that means that these two, the two columns of the matrix B, are linearly independent. And so these are distinct eigenvectors of P, with the eigenvalues lambda 1 and lambda 2 both being 1. Okay, all right, so so we're nearly there. We've got 2 of them, right? They're repeated, or 1 is repeated as an eigenvalue in the in this equation right here, right? Det A minus lambda I equals 0. And so we must have a repeated root in that. All right, so moving on, we want to get the other one. What's the last eigenvalue? Okay, so put another page in front here. Okay, so to show that the third one is 0, what we need to do is show that there exists a column matrix W, okay, so R3, the entries are real, such that this projection matrix P times W is the 0 vector. Okay, because if we get that, then we've got this expression, right? P minus 0 times the identity matrix times W is 0, because this is 0 here. So these two are the same, okay? And so that gives us that that 0 is the third eigenvalue, right? Which you probably already knew, because if you've been watching Yoni's lectures, I believe Yoni demonstrated things like that. I haven't watched them myself, but just looking at the notes from past sessions, I think you've done that. So it shouldn't have been too surprising that this would have been 0. All right, so what we'll do now, I guess I'm actually going to show you explicitly such a W, right? But there's another way to argue this, so don't worry, because this is quite ad hoc, right? You don't know how I would possibly come up with this. In fact, I did some symbolic calculations to realize this. Okay, and then I'll come and show you some other points that you could have thought of as well. All right, so I'm going to say let W1, and this is my first entry of the vector W here. So I'm saying let it be the determinant of B21, B22, B31, B32. Okay, and likewise some similar looking determinants. W2 is negative, the determinant of B11, B12, B31, B32. W3 is this determinant of B1, B12, B21, and B22, right? And then I put them together and say, this is my W. All right, now that I've explicitly got this, what I want to show is that P times W gives me 0, but I'll take a shortcut. So because I can express B transpose just like this, right? I want to multiply B transpose times W. And why did I choose that? Well, it is what is on the right-hand side of the expression for P, right? So if I can deduce that B transpose times W is 0, then I'm basically done, right? That would mean that P times W gives 0. So that's the point of that. Okay, so multiplying those two out, right? So this is this expression here that I've just come up with, in a lot of lines there, but it's actually just this. Now you can easily see that if you multiply those out, you get 0 and 0 in both cases, right? That's not a difficult calculation to just verify. All right, so this means then that what we have is that P times W gives 0, 0, 0, and so 0 is an eigenvalue of P. But what you're actually meant to note, because I mean, you probably wouldn't have been able to think of this in your quiz, right? Even though it's relatively simple. All right, but what you're actually meant to observe is the following: that vectors that are orthogonal to the column space of B are projected onto the 0 vector and hence have an eigenvalue of 0. Okay, so furthermore, any such vector W satisfies W transpose B is 0, where 0 is this, right? And notice that's what I just calculated earlier, right? You don't actually need to know what that W was. So equivalently, B transpose W gives 0, 0, 0. And so again, this is the calculation that I just did on the last page, all right? So in summary, these are the reasons for those 3 eigenvalues, which are 0, 1, and 1, or 1, 1, and 0. Okay, so let's move on and have a look at the next question. We'll have a look at the time too. I think we're okay for time. And I'll get my papers out of the way. Okay, now let's have a look at question 6, which is the last question on your quiz, which says, consider the sequence x of 0, x of 1, x of 2, ... These are vectors in R3, and x of k plus 1 is equal to, this is the projection matrix, times x of k minus 1/2 x of k. And so that's defined for k equals 1, 2, etc., all the natural numbers. So the question says, argue about the value of the limit as k goes to infinite of the norm of x of k Okay, so does it depend on x of 0, or is it the same limit for all possible x of 0? What is that limit? Okay, so I felt a little bit uncomfortable with the notation, to be honest. So I've changed the notation to be subscripts. Just want to let you know, so you, when you see what I've got written here, you don't freak out, okay? But you know, we all have a different preference for the way we see mathematics, all right? So I'll show you how I've written this. So consider the sequence x subscript 0, x subscript 1, and so on, right? So for me, this looks like more familiar, more what I'm accustomed to in seeing a recursive sequence. But yeah, that depends on your background, perhaps, okay? So now it's given by this, right? This is the projection matrix that we've been looking at in previous problems, and it's given by this, all right? So we've got projection matrix times xk minus 1/2 xk, and this is our definition of the next vector in the sequence. All right, and so essentially what we're doing is computing the limit, right? And so you already know what the other parts of the question were. Does this depend on the first one, and so on. Okay, so we need to make a few observations here. So first is that we've got an xk there and we've got an xk there, and why don't we simply combine these so that we get a better looking recursive definition for the next term of the sequence. All right, but this here, that this is the projection matrix, is important because that will allow us to calculate things that we've already calculated and use them here. All right, so what we want to do is let the matrix R be P minus 1/2 I. So in other words, what we're doing is we're factorizing out this xk out to the right, and what remains there is this one, which is the matrix R, and so we're setting that out. Okay, so in other words, we've got this nice simple expression here, xk plus 1 is R times xk. All right, and immediately, this is good because you can obtain a closed form for the kth term. All right, so in other words, let me just show you. So we've got x1 would be R times x0, right? And then so x2 is R times x1, all right? But x1 is R times x0. So you get the idea here, right? You can express that as R squared x0. And so here we see x subscript 2 is R squared subscript x subscript 0. And you can carry this on in the same way and get the general closed form for the sequence, which is xk is equal to R to the power of k x0, right? Okay, now that's good because if you were able to diagonalize this one, then you could calculate this and make the right conclusion about this limit, okay? So that's where you want to go with this. All right, so back to what we've got here. So that's where we're going, but we need to make observations about the eigenvalues in order to use the theorem on diagonalization, right? So in other words, if you know the eigenvalues of the matrix, then they are the diagonal entries of the middle matrix in the diagonalization, and the two outer ones are orthogonal matrices, right? So Q and Q transpose. Okay, but we know the eigenvalues of R because we know the eigenvalues of P, right? So the eigenvalues of R are lambda j minus 1/2, where the lambda j are the eigenvalues of the matrix P. And we know those from the previous calculation, 0, 1, and 1. Okay, so that makes this question a bit more difficult, right? Because if you stuffed up the previous one, then you wouldn't really know what to do here, probably, I would guess, right? All right, so subtracting that half from each of these, we have that the eigenvalues of the matrix are minus a half, plus a half, and plus a half. Okay, so in closed form, we've already deduced this. X subscript k is r to the power of k times the first one, x subscript 0. And so now we can diagonalize this and get a nice expression for for r to the power of k, right? So the diagonalization looks like this. An orthogonal matrix Q times this diagonal matrix, and here I mean there are zeros everywhere else, and then Q transpose. Now remember, well, let's just do some calculations here, right? So we usually use this symbol, an uppercase lambda for this diagonal matrix, right? So we've got this Q lambda and then Q transpose, and this is our R. All right, so let's just calculate what R squared is. Right, so R squared is this, Q transpose, and then we have another one, so Q, and then this, and then Q transpose, right? And this, at this point, you observe what this is, right? This is orthogonal, so, sorry, each of these are orthogonal, so the product of this has to be the identity, right? Because the inverse of Q is Q transpose, because it's orthogonal. And so what we have here is Q times the square of lambda Q transpose. And in general, r to the power of k is Q lambda to the power of k times Q transpose, all right? And that's great because look at what we're looking at here, right? What we want to do is take powers of this, and we end up with r to the power of k is Q times all of these numbers to the power of k, and then just Q transpose, right? But what we should notice here, and it's important, is that each of these diagonal elements of this lambda matrix, they are strictly between -1 and 1. In other words, their absolute value is less than 1. And so as you take higher and higher powers, they go closer and closer to 0, right? So basically the limit as k approaches infinite of r to the power of k is the 0 matrix, right? So in other words, this. So it's still 3 by 3, it's a 0 matrix. And so if we're multiplying this times x0 here, well, we know that the limit of this one, this goes to 0, right? And so then the limit of the norm of xk has to be 0, irrespective of the value of x0. Okay, so I believe that answers that question sufficiently, and maybe I've gone into too many details, but I don't think that is a problem. And so I think we're ready to turn it over to Walla, who will basically introduce you to your task for the project, all right? Thank you, Walla.
Yeah, this is about your final project. In your final project, there is 6 different topics. You need to choose just 3 of these topics, which you like, something which you are familiar with that. You need to make, or you need to do 3 things. The first thing, you need to write a page summary and try to write it in a good way. And if you don't know how to write it in a good way, you can ask your friend to write it and to become tidy. So this is the first thing. You need to choose a topic, and you need to write a page summary about this topic. And the second thing you need to do, you need to write a Jupyter notebook with 1 to 3 code demonstration of the results and method of the topic. For example, if you talk about classification or BCA, try to run 2 or 3 codes to show how this method is working. Okay, this is in part 2. And in part 3, you need to make a YouTube. This YouTube, not more than 8 minutes. You need to take one of these 8 topics, and you need to show Julia code, and you need to explain about how about one of these. This is about your project. So you need to submit all of these in one file. Now we need, today I will discuss with you classification, which is here topic 4. What we need to do in classification, here they give you a hint in each question. In topic 4, classification, the question asks you, how does least squares classification work? We need to show how least square work for classification. You talked this before in your lecture on Monday, but today we will go briefly about classification. In general, if you have a data here between x and y, and we have random point, we try to find the best line, and we try to fit this line with the data. The easiest and the familiar method which we can use to find the least square, which means the difference between observed point and predicted point. So you can find the value, you can find many lines, and which have the line which make the difference between observed point and the predicted point is small, which we call that this line is the best line. And if we are in 2 dimension, we need to find the value of B0, and we need to find the slope, which is B1. But if we are in 3 dimension, we have more than parameter. This is the main idea. For example, if you need to fit the data. Sometimes, if you have a data in this shape, and you try to fit this data, and you find that this line passed to all points, this is overfitting. Why is it overfitting? Because this is work just for this set of data. In machine learning, we have training set, we have also testing set. It is good for it's working well with the training set. But if we have another point, this curve will not give us a good prediction about another point. Okay. So the idea, if we need to fit the line, is to predict the value of y. If you need to find the parameter B0, B1, and B2, if we can find the value of y, which equal B0 plus B1x plus B2 x squared. Okay, if we have 3 parameters, and you did this before in your lecture, we can write this as 1x and x squared multiply with B0, B1, and B2. If we suppose that the matrix A is a design matrix, because here we have just 3 different variables, the matrix A consists of 3 columns. We have here 1. Here we have x1, x2 up to xn. And in the third column, we have x1 squared, x2 squared up to xn squared. And you learned before how to find the value of these parameters by using least square. And to find the value of b, we need to find the value of the norm of ab minus y. And we need to minimize this norm. And you get that the value of b equal A transpose times A, and this is inverse, multiply with A transpose Y. And we call it that as A diagram Y. Now we need to fitting a model to a data where the outcome takes the value 1 or minus 1, true or false. For example, if someone have a specific disease, we said that if he has this disease or not. For example, also, if you received an email, you need to show this email, is it spam or not spam? This is the mean of classification. So in general, to fitting a model to a data, so the outcome may be true or false, maybe yes or no. Because here we have just 2 values, we said we call it Boolean classification or binary classification. If we have just 2 outcomes, yes or no, or 1, 2, for example, male and female, we call it Boolean classification. So the goal of data fitting is to predict the value of y. In In general, if you have any function, the function is go from Rn to R if you have any function. But in this case, the function is goes from Rn to 1 or -1 to yes or no. Okay? In your lecture, you have an image and you try to classify this image. You use many different packages like MNIST, you use Flux, I think, and data. MNIST, we use MNIST, it's special for pictures because it's split the data into training data set and testing data set. And you use data 3 for positive and 8 for negative and try to decide if it is 8 or 3. And after that, we can find the value of prediction error. We have four different types of prediction error. We have a true positive. The mean of a true positive when the prediction is the same as the observation. When, for example, y is positive and y hat also is positive. We have also true negative when y is negative and y hat also is negative. So we have for different types, we have a true positive when y is positive and y hat is positive. We have also true negative when y is negative. Y here, this one is observed and y hat is predicted. Here, this is observed and this is predicted. If we have here y equal -1, which means the observed here is negative and y hat also is negative, here the predictive and the observed is the same. So we call it a true negative. We have the type which we call it false positive. If the observed value is negative and the predicted one is positive. In this case, we call it type 1 error. In statistics in general, there is type 1 error and type 2 error. This is will give you type 1 error. If we have false negative, that means the observed value is positive and the predictive value is negative. This is which we call it type 2 error. Okay? So the idea in classification, just the output all the time is 1 or 2, positive or negative, maybe 2. If you have 2, we call it binary, or maybe more than 2. To learn more about the classification, you can go back to VMLS book, chapter 13, and chapter 14. You will find more explanation about classification in chapter 14. And you need to build the code. To build the code, you will use some packages like Flux, like MNIST, and data. And sometimes you can find the value of confusion matrix. Okay, this is a brief idea about classification and how classification is work. So you need to write 1 page about classification. Try to go back to chapter 14 to read deeply about classification and to summarize just 1 paper about classification if you are interested in this topic. And you can, for example, upload an image or anything you want to classify and split your data into training set and testing set. Then you need to decide the output. The output should be, for example, in your lecture was 3 and 8, 3 for positive, I think, and 8 for negative. And here in this case, we have, for example, 1 and -1, 1 for positive, -1 for negative. This is the main idea for classification. Okay. This is the end of this lecture. Next week, we will discuss about the rest topics, topic 2, topic 5, 9, 11, and 12. Have a good night.
Spam.